Three. She said three.
Chapter
Y'all.
3.
Uh-oh.
We're going to learn about electromagnetic and particulate radiation. So basically, the electromagnetic spectrum. It's not a long lecture, by the way. Is it hard? Could be, yes. Yes, more math. It's physics, hello.
Love that.
So, we use, we know about both ends of the electromagnetic spectrum used in medical imaging, right? So on the lower end of the electromagnetic spectrum, what do we have? Did Mr. Fong go over that?
Short,
Okay.
short waves or something?
So, electromagnetic radiation, what is it? It's basically any magnetic disturbance in space. So, the theory was developed by John Maxwell
Okay.
in the 19th century. And he said these four things, or these four principles, apply to electromagnetic radiation. He said that all electromagnetic radiation is similar. They don't have a mass. The energy is carried in waves, and they travel at the speed of light. So I was wondering, how is it both electric and magnetic? And I did some research, and apparently they say, well, we already know that X-rays are created after we pass an electric current through it, and every like electricity that we use on the daily, without or to our naked eye we can't see it, but there is a small magnetic field that's also created because of this electricity. So electromagnetic radiation is both electric and magnetic.
This one here. So it means anything with a charge, therefore has like magnetism as well?
Yes,
Okay.
it has properties of magnetism. For example, we know that every single thing is made up of atoms, right? And each atom has a nucleus made of neutrons and protons and electrons that orbit around the nucleus. So electrons are tiny moving charges or particles, right? They have a negative charge. So when they're orbiting around the nucleus, they create a small magnetic field. So even in the subatomic level, they do have a magnetic field that's created. Yes.
So the electrons are the ones responsible for creating the magnetic field in the electromagnetic.
Yes. So any moving electric charge will create a magnetic field.
You said any electric charge?
Any moving electric charge will create a magnetic field. Ready? So, this is the electromagnetic spectrum. On the lower energy side, we have our radio waves and microwaves. And then all the way towards the end, we have our X-rays and our gamma rays. So, if I ask you which one has the highest energy, it would be gamma rays. So as we go from left to right, the energy increases. And if you take a look at the frequency, see how it's more frequent here?
Mm-hmm.
So as energy increases, our frequency also increases. And And we'll talk more about the relationship between those in a couple of slides,
So it increases from right to left.
from left to right. The important thing to understand is that all of these different waves, they all have the same velocity as the speed of light. So they're all similar in that way. But where they differ is that they have different energies, they have different wavelengths, and they have different frequencies.
What's the symbol for frequency again?
I'll tell you in just a second.
This
Yes.
energy increases or with moving towards the right?
So you see how the wave is kind of like there's 1, 2, 3. There's about 3 waves here, and over here there's more. So we have more frequency on the right side of the spectrum. So as energy increases, our frequency goes up also. And another important thing is that only high energy radiation, like our X-rays and gamma rays, they are able to ionize matter. And what does ionization mean? The removal of electrons. And what's the speed of light?
3, 10 to the power of 3.
Right. So this is the order from lowest to highest energy. The lowest we have are radio waves, then microwaves, infrared light, visible light, ultraviolet light, and then X-rays and gamma rays. Lowest to highest energy. So if I ask you which one of these has the highest frequency, what would your answer be?
Radio waves.
Gammas.
Radio waves.
Highest
Frequency.
The lowest
High
one.
frequency, yes.
Yes,
Gamma.
gamma rays.
So if she said wavelength,
Yeah,
that would
that is
be
the.
radio waves.
One question.
Yes.
So would airplanes be before X-ray when you're in an airplane?
Airplanes?
Yes. You know how you get radiation when you're in an airplane?
From the UV light?
Uh-huh. So it would be before.
Yeah, it would be before.
Damn, that's bad.
It's just a KUV.
Infrared.
Lasers?
Yeah, lasers. I was in my head, I'm like, those green and red lights.
The ones you point at cats, right?
Yes. Yes, thermometers. EDC.
What is the examples of the infrared?
Everyday
Yeah,
camera?
like infrared light is the lasers. So if you go get laser hair removal, you're getting some radiation.
Do we need to wear a dosimeter for that, or?
No, Jay. He would ask that question.
Yeah.
He's gonna be like, it's okay, I'm an extra tech, I can do this.
I do the math.
Alright. So, before we get into some math, we need to understand what wavelength is, frequency is. So parts of a wave. Up here at the top, we have the crest. Easy to remember, right? And then here, the valley is what we call a trough. So we have a crest, peak, and a valley, trough. Amplitude is the height of the wave. So from this black line all the way to the top of the crest. That's our amplitude. You don't need to worry about elevation. Wavelength is the distance from a crest to the next crest, or it can be the distance from a trough to the next trough. And then last but not least, we have our frequency, which is the number of wavelengths that pass a given point at 1 second.
So is the crest on top and trows are on the bottom?
Yes. So what is the frequency of this wave? 2.
the half?
It has to be a full wavelength, so don't worry about the half.
You said don't worry about the amplitude?
No, don't worry about the elevation.
Oh.
Wait, how is it two again? I'm sorry.
You count the crest.
So frequency is a number of wavelengths. And what is a wavelength? Basically the distance from a crest to the next crest. So we have a crest here, we have another one here. So 1, 2.
So will you ask frequency of the crest? Because it can also be a trout or whatever that word is.
Wait, say that again?
Hey, would you ask what is the frequency of the crest? Or, because you know how it says distance from the crest or trout to trout.
No, I would ask you frequency of wavelengths.
Already at it?
So why is
But
this?
wavelength can be crest or the bottom one, right?
Yes, from crest to crest or trough to trough.
There's only one, I see.
1, 2.
That's only one.
Uh,
That's it.
What about the trail? It's 3.
See, one is gonna be.
So this is a wavelength from here to here and here to here,
I see.
right?
This is two.
But those are halves on the ends, so we don't count those, right?
Or do they make up the
Okay.
whole?
Yeah,
Two
don't
crests.
worry about the halves.
So only if you count the halves, you can get two crests also, and the two wavelengths on the top. Otherwise, you get only two wavelengths on the bottom.
What?
Meaning one crest, one half makes two, one, and then that one is two. So you have two wavelengths is showing down, but up this will be showing one.
So you won't say the 3 throws? Wavelength of throws?
No,
I'm not gonna ask you questions like these. They're confusing.
I just got
For
confused
now,
by
just
Shaheen.
know that a wavelength is the distance from a crest to the next crest, or from a trough to the next trough. When you have formulas, it's gonna be actual numbers. I'm not gonna ask you to bust out your ruler and measure.
Thank God.
Hmm.
I was tripping for a second.
Okay,
Did you already send this to us?
no, Dawn, we just started distracted.
You know, Mr.
Like I
Frank.
barely put this together 10 minutes ago.
You shot?
I told you I was stressed. Ready?
No.
Hey man, to be honest,
The whole diagram over here.
I drew too.
it's
But Matt, you have this for us already,
She said I got it though.
Even though it's in the book, I
but you'll give it to us, no?
It's in the book, right? This picture, or no? Everything's on the book.
It just has like the wavelength, the frequency, and the amplitude, but it doesn't have like, you know.
It's all right, I'm not
Page
gonna rush.
28.
Thank God.
Take your time,
Did you say what's up?
What's that your pen?
Oh, this
Yeah,
one here?
frequency is the number of wavelengths.
No, I don't use this. Do you want it?
Yeah, no, I put that because, you know.
It's all good.
It's all good.
So what was the shorthand like symbol for frequency and wavelength?
We're getting there, Jay. Simmer
Hold your
down.
horses, Jay.
I'm sorry.
Questions at the end. So,
What did she say?
if you notice in this little chart, the longer the wavelength, right? We have longer wavelength here compared to here.
Mhm.
What do you notice about the frequency?
More frequency.
Less frequency. Like for example, here we have 1, 2, 3, 4 crests in that amount of distance.
Mhm.
Here is like only 1. So the wavelengths are longer and the frequency is shorter.
So what was your question? You said, what do we notice about what?
What do we notice about the frequency here
Okay,
versus here?
so on short wavelengths, the frequency is higher, and on long wavelengths, the frequency
Frequency
is
is lower. Mhm. So you can say that wavelength and frequency have what kind of relationship?
Inverse.
Inverse.
And then frequency and energy have what kind of relationship?
Direct.
Direct.
You said short length, short wavelengths.
So longer wavelength
Mhm.
will have lower frequency.
Okay, gotcha.
and lower energy.
For a long wavelength?
And then shorter wavelength is higher frequency and higher energy.
I'm sorry, can you repeat that again? Longer wavelength will have.
Longer wavelength has lower frequency and lower energy. And then what about shorter wavelength?
Higher frequency.
Higher frequency and more energy.
Yes.
And what did you say have a direct relationship?
My mind is frequency and energy are direct.
And wavelength and
Wavelength
frequency
and
are
frequency are
inverse.
inverse or indirect. Everyone good so far?
Mhm.
Where did the colors move?
I feel repeated.
Don't worry about it. All right. Yes, so some relationships that you guys have to understand. Amplitude, what did we say amplitude was?
The distance from
line.
bottom to the top of mountain.
Correct. Okay, so as amplitude increases, the intensity increases,
Mm.
okay?
So the intensity of the energy.
Mm-hmm.
Okay.
So compared to radio waves, will X-rays have a higher amplitude or a shorter amplitude?
No, higher.
Higher, because X-rays are more intense.
Oh.
Remember, higher energy? And then we already covered these last three. As wavelength increases, does energy go up or down? Down. Because as wavelength increases, it's gonna be like 1, 2. But if it's a shorter wavelength, it's gonna be like 1, 2, 3. So as frequency increases, energy goes up. Wavelength and frequency are inversely related. So I have a question for you guys. When we compare infrared light and gamma rays, which one has the shorter wavelength?
Gamma rays have shorter wavelength.
Infrared has shorter wavelength.
Why, ma'am? It comes before in the thing. The
So
wavelength,
infrared, does it have higher or lesser energy than gamma rays?
I think it has less
Less
energy,
energy.
less wavelength. I think this is coming everything
Okay, so
Wavelength
will the
is
wavelength be short or long?
longer.
Exactly.
So I see.
But what about energy?
One.
Yeah, which one has higher energy comparing infrared?
Gamma is
The
higher.
gamma rays.
Gamma has higher energy. Okay, time to draw.
So gamma has higher energy, which means it
Is there
has
a marker
higher
here?
frequency. But a shorter wavelength, right?
Yes.
So basically anything that's high has short wavelength.
You know what I'm talking about? So, hey, you know, at the end of the movie, that guy thinks it's on to the
So, this is the wavelength. And look at the wavelengths here.
Oh, yeah. That's what I'm thinking about. There you go.
Sorry. Make sure you call me properly.
Or we could post call me.
What? When you ask, like, people don't know that?
Does that make sense?
Yes, ma'am.
So we have shorter wavelengths. See, the distance is very short. We have more more frequency of the waves, and then we also know that more frequency means higher energy. And compared to here, the wavelength is longer, so the frequency goes down, right? See how we have more waves here compared to here? And then that also means the energy is lower.
So this measure, are you saying that amplitude and intensity are the same thing, or the amplitude is low?
So as the amplitude goes up, the intensity increases. Amplitude meaning like the height of the wave. So as the height goes up, that means it's more intense.
Here, the same.
It's not trying to tell you that amplitude and intensity are the same. It's trying to show you that it has a direct relationship. All right, so these little symbols you have to memorize. Sorry,
Can
not
you,
sorry.
Can you move the? Thank you.
You got $3.
Ooh, this guy's on my phone. $3.
Which one? Oh, okay.
Oh no.
Oh, man.
Someone help?
You broken, Miss Bonilla? It's coming right off.
Oh,
Ooh.
Jay, where the hell?
She's on the edge.
He's like, feel the edge.
He said she got this shit.
No. If you sit on the aisle row or in a plane near that exit, what do they expect you to do?
Move. Get out the way. Move.
I hope it stays.
Oh my God! Oh no!
You're doing the most.
it's gonna fall on me.
You don't follow me?
Ma'am, can I just see that other screen from the furnace one? Because you said that copper is not. Thanks, ma'am.
Got it?
Yes, ma'am.
So energy is measured in electron volts, EV. Frequency, F, is measured in hertz. So that when you're talking about frequency, that means per second, or how frequent it is. You know what I mean? So if I say this wave has, or this radiation has frequency of 10 hertz, that means 10 wavelengths per second. And then wavelength, the symbol is kind of like an upside down Y. Wavelength is measured in meters. Velocity, it has a symbol of C, which is equal to the speed of light. And if you take a look at the numbers, you can see that they're all continuous. It doesn't go from 10 to the power of 5 to 10 to the power of 50. It's all continuous.
All values are continuous of velocity.
So all the values that you find on the electromagnetic spectrum, they're all continuous. So like for example, it starts at 0, 1, 2, 3, 4, 5. It's all continuous. There's
Energy
no
is continuous.
break. Yes.
Or frequency is also.
So wavelength is measured in what? Meters. What about frequency?
Hertz.
Hertz. Okay. What does C mean?
Speed of light.
Velocity. And when we talk about radiation, it's going to be the speed of light.
Yes, ma'am.
So if I ask you what's the velocity of gamma rays,
G rate and to power 8.
what's the velocity of microwaves?
3 to
Also C.
Yes. So all electromagnetic radiation have the same velocity. Good. Alright, so we have some fun formulas to remember. Formula for velocity, if you guys remember from chapter 1, it's velocity equals frequency times, what's this symbol?
Wavelength.
Wavelength. But if I ask you, when we're talking about electromagnetic radiation, the the formula for velocity would be a little bit different, but it's really not. It's going to be C equals F times wavelength. What is C equal to?
Speed of light.
Speed of light. So we already know the velocity, so we can plug C in there. And then F times wavelength.
It's just synopsis, right?
Synonymous, exactly.
Frequency.
Yes.
So does that explain the answer?
Oh, okay. On this test, it gives me an option to provide the scientific calculator for you guys. Did you guys, like, use
Yeah,
it
we've
on
used it
other
before.
tests?
I use my own.
Oh, okay.
Well, I put these on. Maybe you need to show us, like, how you, like, where to go.
Yeah, cause it's kinda, yeah, it'd be throwing me off. See,
Yeah, I'll show you for the next test.
Will this one work?
Yeah, if it's scientific, you're good. So, question. What is the frequency of electromagnetic energy with a wavelength of 1 times 10 to the negative 11 meters? So, what's the formula for velocity?
Frequency times wavelength.
Okay, and we can always rearrange the formulas according to what we need to figure out, right? So, in order to find frequency, we're going to take C and then divide it by the wavelength. And do we already know C?
Yeah, 310 to the power of 8.
Okay, and then wavelength is this amount right here. So, and when we plug that into the formula, this is gonna be our answer. Sorry, here. So we take 3 times 10 to the power of 8, which is our speed of light, divided by our wavelength, 1 times 10 to the power of negative 11, and our answer is going to be 3 times 10 to the power of 19 hertz. Did I lose anyone?
Yeah, why do you have a shouldn't it be negative?
Okay. What do you mean?
Well, you have negative 11 and positive 8. It's
Okay, so the question is, what is the frequency of electromagnetic energy with a wavelength of this much? Okay? So we have our formula here to figure out frequency. Okay?
Monty,
C, what is C?
we won the
The
point.
speed of light.
Velocity.
Velocity of electromagnetic radiation, which
We won
is
the plate.
speed of light. Okay, and then they also give you the wavelength, right? So all we need to do is plug that in. So F equals 3 times 10 to the power of 8, C, divided by our wavelength.
So they're gonna give you the weights.
Yes.
So wavelength does not have like a set.
No, it can be, and remember that chart that I showed you? It has all different kinds of wavelengths. The only thing that stays constant is our,
Speed of light.
yes. And then frequency is always going to be expressed as hertz. Shamika, you good now?
Okay, I got my, the frequency, I understand, I know it's F equals C divided by A. So we
Okay.
always will take, oh, never mind, I got it, there you go.
You got it?
Yeah, it clicked.
Okay. Yeah, anytime we're talking about electromagnetic energy,
Uh-huh.
it's always going to be speed of light.
Okay.
Alright, did Mr. Fromm go over wave particle duality? No, okay. So, up until this point, we understood that radiation or electromagnetic energy travels as a wave. But it has, let's say it has multiple personalities. It can either be a wave
Bless you.
or it can behave as a particle, depending on what matter it's interacting with. So electromagnetic energy does not always act like a wave. Sometimes it acts like a particle. So it depends on its energy and environment. So there's no incorrect way to describe electromagnetic radiation. It can either be a wave or a particle, depending on the environment that it's in.
Electromagnetic energy is
Mhm.
either a particle or a wave.
Yes, it can travel in waves or as particles. So what is a particle of X-ray known as?
Electron.
Photon, right? Photons are tiny particles of light. So you can describe electromagnetic energy either as a wave or as particles.
Repeat that. No, I just wanna make sure I heard you clearly.
Sorry. So, yes, my throat is sore. Oh, so, we know that any matter is made up of tiny individual particles called atoms, right? So even with light, or electromagnetic radiation, they still have tiny little particles. So with X-rays or light, the tiniest particle of light is called a photon. So that's kind of describing this wave particle duality, that electromagnetic energy can be described as a wave or as tiny particles.
Not a specific tiny particle, but just tiny particles.
So the tiniest part of light is called particle.
Photon.
Oh, photon. I knew that.
Gamma rays, is that also?
I would assume so, but I have to double check.
So electromagnetic radiation can be described as a wave or a particle, right?
Okay, so before we get into what this formula means, there was a German physicist whose name was Max Planck, and he had nothing better to do other than do experiments on light and radiation. So he was studying something called black body radiation, and it was a special device that emitted light at all different kinds of frequencies. And no one could explain how is light able to be emitted at all of these frequencies perfectly. And he came up with this theory that light or electromagnetic energy could only be emitted in little packets of energy, okay, which they now call quantum or quanta. So he came up with a formula to describe how are we going to figure out the energy of electromagnetic radiation or waves or whatever. So he came up with this formula, E equals HF, and the H is known as the Planck's Constant because it was Max Planck that came up with this. And what that H represents is that the amount of energy that a photon, the tiniest particle, is able to carry at a given frequency. So that's kind of like our base, energy that, atoms can, transfer energy at. So it's a number that we came up with to describe, atoms need this much energy at this frequency in order to transfer energy. So that number is going to stay constant anytime that we use this formula.
So the Planck's constant is the amount of energy a photon carries at any given frequency.
Yes.
Just making sure.
Yes. So if we give you a formula to ask you to calculate the energy, it's going to use Planck's constant, because that is that base energy that atoms must have in order to transfer energy. So that number has to be the base number in order for any transfer of energy to happen. I'll tell you in just a second. Okay, so H is Planck's constant, and this is the number. It's going to always be expressed in EV seconds. This is just an FYI, you don't have to memorize this. This is just the SI units version of this one.
So you're doing the standard unit.
So 1 photon of light or electromagnetic radiation is going to have this much energy. So the tiniest particle of electromagnetic radiation is going to have that much energy at any given point. So if the frequency increases in the electromagnetic radiation, then our energy is going to increase, right?
But the Planck's stays constant.
Yes, that's like kind of like the base number of any particle of electromagnetic radiation. They have that much energy at all times.
EV is like, electron volt.
Say that again?
EV is not.
Yes, electron volts. So to summarize what I just said, to calculate the energy of electromagnetic radiation, like microwaves, gamma rays, X-rays, blah, 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 this is the formula that we use, okay?
Planck's
One more.
constant is the constant for the value of energy for
One particle of electromagnetic radiation, or photon. So if I ask you, for example, how much energy does 1 photon of X-ray have?
4.135.
Yes. Alright, last slide for today.
Like the way, the speed of light is always that one, that H is always gonna be
The same.
the same thing.
Yes. So, to give you guys an example, so you guys are not completely lost, a question would be something like this. What is the frequency of an X-ray photon with an energy of 80 keV? Okay? So we have to set up the equation. So we already know the energy in this equation, and we know what H is, because it's Planck's constant, right? So now we need to figure out what F is. Well, first we need to do what?
It's
F by
convert
itself.
that
Before
into
that.
electron volts,
Okay.
right?
So we need to convert that 80 keV to electron volts. And we already know what kilo stands for, which is 1,000. So 80 times 1,000 is 80,000, okay? And then we know H is our Planck's constant, so we're just gonna plug it into the equation. So, if we were to write it exactly as the formula says, it would be 80 80,000 EV equals our Planck's constant times our frequency. And then divide both sides by our Planck's constant, which is what is written here. 80,000 divided by our Planck's constant. And that would give you the answer to what our frequency is.
Are you
Did-
sure we can get F by itself by doing that? Cause I did it the last time with that, Mr. Fung said I was wrong. That's only doing H by itself. But if we're trying to get F by itself, that I couldn't do it.
You can do it like that, yeah. It's just like cross multiplication. Is anyone confused?
Is there a worksheet?
I can give y'all some worksheets. Yes.
May I have these slides? If we're gonna like,
What I can do is make some worksheets with some examples,
Yeah.
so you can practice.
Yeah, that'll be very helpful.
Yes.
Where does 1,000 come from?
Which 1,000?
You said 80.
Kilo.
So you have to compare.
Kilo.
Oh shoot, I'll be
So
forgetting
you
about that.
multiply 80 times the 80 times.
Hold on, let me explain it to her. So, what is 80 keV?
Eight,
The energy.
80,000.
Okay, yeah,
Okay.
I got that one.
So we're gonna plug that into our E here.
Mm-hmm.
But how do we express our Planck's constant? EV seconds, right?
Okay.
So that's why we need to have both of the units similar. So in order for us to do the math, we have to turn this into EV also.
So EV is 1,000.
So kilo EV, kilo means 1,000. Like
Oh, yeah.
1 kilogram
Okay.
is 1,000 grams.
Gotcha.
1 kilo electron volts would be 1,000 electron volts.
Gotcha.
That's why we take the 80 times it by 1,000. We get our 80,000 here. And then we divide it by the Planck's constant.
Gotcha.
And make sure your units are the same.
Yes.
So on here, I put energy.
Milli is also 1,000.
Mm-hmm.
Milli is also 1,000.
no.
Yes. Y'all get a better understanding once you actually do the problems with the formulas in different kinds of ways.
It's 1,000 in the other direction.
Will
What do you mean?
will you ever have
So like divided by 1,000?